quickly introduce the class for those who are new here. Basically, the plan for today is going to be to go through and continue on with our circular function related stuff. We were previously last Monday looking at the sketching of sine and cos. Now we're going to move on to tan. But before that, we are going to go through some student submitted questions. A big part of that program, for those who aren't aware, is that you can submit questions ahead of time, and we'll go through those during the class. That way everyone's getting what they specifically need. So I've got that on the screen share right now. Also, for those who are also new, if you check through the meeting window, you'll eventually find a camera that's just sort of aimed at a white screen. Currently got my hand resting there. If you just pin that, that's what we'll be doing our handwritten notes. So if I go through and do any work solutions written out, that's where you'll see those. So go ahead and just right click and pin that, so it's easier for you to ping back and forth between the screen share window and the working out window. So this was the question that was submitted to us. I got that on the screen share. I don't know how readable that is. Can I zoom? Yeah, that's a bit better then. Cool. Okay, so we have a function, x natural log x minus x. First question, find f dash. For those who haven't done derivatives yet, this is just finding the derivative. It's assumed that this was tech-free, so if we think about how we would find the derivative, for those who have done it, what might be involved in finding the derivative of this?
The product rule.
Product rule.
And the sum rule.
Yeah, so what's the other one you said, sorry?
The sum rule.
The sum
rule. I forgot what it's called, but it's the one with the sums.
Oh, yes. Yeah, no, I get what you mean. Yeah, where you have the two functions submitted, separated by either a plus or a minus, you basically just work on those individually. Yeah, that's precisely what's going on here. In the interest of time, we'll just cas that out just so we can get it, because part C is going to be the main thing to watch here. So let's go ahead and do that. One function is equal to x times natural log x minus x, and then we're just going to diff that out. Cool, that's kind of interesting. We get down to just regular old natural log x. Cool. Hence find the exact value of that related integral. Again, assuming this being tech-free, what kind of thing might we be doing in this circumstance?
Just subbing the values.
Subbing the values. Oh, right, that's... Yeah, Oh, well, hang on. You've got to be able to anti-diff the log. Hang on. I think diff of log goes to 1 over x, but anti-diff of log does not. Anti-diff of log, I believe, doesn't have a thing that you can directly just plug in. Unless it's cas, obviously. Cas, you just plug it directly in. In a tech-free way, though, anti-diff of log gets you back to the function that we just had. Alright, so if I go ahead and anti-diff natural log x, this is not something that you have access to on your formula sheet. You have to find your way back there by other means. So assuming tech-free, what do we do in this circumstance?
We sub in 0 and natural log of 2 into that, like natural log of x. So x natural log of x minus x.
Yeah, we're going to sub it into that one specifically. Because what's going on in this question is there is a relationship being drawn between f of x and f dash. Right? So f of x being the original function, f dash being the derivative. When you anti-diff the derivative, you should get back to the original. So when we're looking at doing the anti-diff of natural log, we're going to go back to f of x. That's getting our capital F, for other words. And then completing the definite integral, which would be a matter of shoving in the upper bound and lower bound. Again, just to skip the math regarding it, I'll go ahead and cas that out. So again, using that original function, it would be e squared, and then h of 1, because it's top take bottom. And that'll get us our value for that. Now for the harder part. Part C. Consider the function g, and it's a product of an exponential and a log. Using a suitable substitution or something, evaluate e to the x g of x. Okay. So e to the x g of x, if we think about what that is just based on the definitions, if g of x is that exponential multiplied by that log, and we also have in our integral e to the x times g of x, what we basically have is the exponentials will combine into each other. Because what you'll have is, if I pull this down, you'll have integral of e to the x, and it's now being multiplied by e to the 2x, natural log e to the x plus 1. So one way you could possibly go about it is condense those down, and that would be a start. Now we have to do this between natural log of 2 and 0, so we need to be able to do our antidiff first. Okay, so what are we going to do from here? Okay, we need to know how to antidiff this function. There's a lot going on there. Where's the similarities? So we knew from the part B, natural log, that the relationship between that and the f of x was a diff-antidiff relationship. Considering that this is part C, it's probably relying on something similar there. Let's see, where do we go from here? Natural log, well, natural log x, we can bring that down. Oh yeah, anyhow.
So this is supposed to be a integration by recognition question?
That's what I'm sort of assuming, based off of the sequence of questions. So using a substitution, trying to make this look more like what we had, I could replace, like for instance, u as the brackets of the log, and that will get us closer to the integration we had from earlier. So if we say u equals e to the x plus 1, we would now have integral natural log 2 0 e3x natural log u, and that gets us a bit closer. What else could we do instead? Still not great. We now have both u's and x's in them. What this is reminding me of is another kind of topic, which is, if I pull up the lecture notes regarding what I think is going on here. Rules of integration, I think it's this one. So let me change that screen share over. Where is it? There's this thing about integration by substitution, which is what you can do to find the integral of any composite function. And you follow a sequence of steps as per this list here. So to give an example of what that might look like, we'll have one like this. Alright, so you have ax plus b to the power of n. This is not something you can naturally antidiff. The idea behind this is to convert your entire integral into a simpler integral which has a new variable in it, and only that new variable in it. So for instance, in this case, it'd be a matter of replacing the entire ax plus b with just the letter u. And the reason why is because that brings this more complicated function down to just a simple power function. From there, we use the relationship between the derivative and the original function. We want to find the derivative of that u, this function that we've now created. So derivative of a linear, in this case, just gets you the coefficient. From there, you do something that's a bit weird. You rearrange the derivative equation itself. This is an equation. You can kind of treat this like a fraction. And the reason why we're doing this specifically is because if you just replace this with u, you've still got dx in there. What you want to have is du. And so to replace dx with something that has du in it, you need to have an equation with something that has du and dx in them, which is why we're rearranging this to get dx on its own. We're going to replace the dx with what it equals, and we're going to replace the inside of that bracket with what it equals. Because in doing so, what you get is a function that is a lot easier to antidiff. We know how to antidiff a power function. You just raise the power and divide through by that raised power. That's what this is reminding me of. Once you go through the antidiff process, you just replace the u back where it belongs. The challenge I'm seeing with this question is that it has a product rule related thing in there as well. You have e to the x in there as well, which is a bit more challenging. So my assumption is that there's going to be some sort of play between those, which is why I've started by replacing the inside of the bracket of u, of e to the x plus 1 with u. Now, to go from there, what could we do? Perhaps instead of replacing e to the x plus 1 with u, we just do e to the x. I think that sounds a bit more useful, because if u is e to the x, then not only can we replace most of the inside of that bracket, but we can also replace this. So instead of it being e to the 3x, it's now u to the 3. All we're going to do from here is replace dx with the equivalent du, which means diffing this. So du dx also happens to be e to the x. Oh shit, this is going to recursively go over and over again, isn't it? Maybe not, maybe it'll be fine. Rearranging for dx, you now have du divided by e to the x is equal to dx. So instead of writing dx in that spot, you can now write 1 over e to the x du. Now from here, we still know that e to the x is the same thing as u. So once again, replacing that with u. And then finally, natural log 2, 0, the u's cancel down to u squared. Natural log u plus 1 du, which ends up being significantly simpler than what we had before, but still not quite there, because we still can't really antidiff u squared natural log u plus 1. So what are we going to do from here? That's probably as far as I could get this now. I'm not entirely confident I'll be able to take this to the end today, but now that I have a copy of the question, I think what I could do is I could work on this more in my own time and see how I can get it from here. But hopefully that's at least given you something to get you further than where you were before, using those steps regarding the integration by substitution. Because the next little bit in here would be figuring out how you get, I guess, the antidiff of this. It's getting closer, but still not quite there. So I think leave that one with me. I'll keep going at it, and then either I'll message you the full solution that I have, or in the next class I'll cover it live. What do you think?
Sure, okay, that works.
Cool, okay. Does that help so far regarding getting things a bit simpler?
Yeah. Yeah, that's much more than I imagined.
Yeah, for sure. It's this one was it looks like there's going to be a lot involved in this. Where'd you find this, by the way?
I just searched up like hard BC integration questions.
Yeah,
So yeah.
fair enough, fair enough. Definitely a hard one for sure. But yeah, hopefully that gives you something to work on while I also have a work on it as well on the back. But okay, cool. On to our regularly scheduled programming. So, tan graphs. Again, as I said in the beginning, we were looking at sine and cos and sketching of those. Tan is oddly enough quite different to the others. The reason why is because tan is the division between sine and cos. That is what it is by definition. And whenever you have division between functions, you have the possibility of your denominator going to 0, which is expressed graphically by vertical asymptotes. If we think about like the hyperbola, for instance, 1 divided by x, the reason why that has a vertical asymptote is because when that denominator of x goes to 0, you get undefined, and undefined appears as asymptotes. So it shouldn't come as too much surprise that the graph of tan x has a sequence of asymptotes. The reason why it's going to have that repeated structure is because sine and cos are themselves repetitive over time. See a question? Bit confused that we're going over only 10 in this class. Told over integration. So the integration related stuff, that would be on the Tuesday and Friday classes. And if there are any like super important things to cover that you wanted to, you can submit questions for any of these classes and we'll go through that, which is why we're covering the integration related stuff just at the beginning there. But yes, Monday is primarily going to be Unit 1 and 2. Tuesday is primarily Unit 3, 4, and so on and so forth. Does that answer your question? Cool. Okay, so yes, graph of tan. Now, I teach this a little bit differently as to how we sketch this. In the book, you'll notice there are a sequence of equations that can help you get these. They have like this 2k with pi in it, and a sequence of that stuff. I think the challenge with those is that you have to learn a different set of equations depending on what the graph looks like. Whereas if you look at how, if you cover the way I cover it, or solve the questions the way I'm proposing that you solve it, it's the same sort of procedure over and over again. You're not actually needing to change up how you do things. So, the graph of the tan itself, you can kind of think of as a repeated sequence of cubic kind of functions, all separated by those asymptotes. There is an inflection point that will always be at the dead center of each of those separations of asymptotes. Note that it's not a stationary point of inflection. It still does have a net positive or a net negative gradient. It won't actually be 0. So if you're trying to find those spots by solving, for instance, derivative equals 0, you're not actually going to find those spots there. But they will always be at the dead center of your asymptotes, no matter what, so you can always find those using a midpoint equation. As for how each of the terms impact the shape of the graph, the dilation factors obviously do impact it, but it's unlikely it matters, because if you look at what it does, it simply just stretches it in a certain way. And it's highly unlikely you'll ever have to sketch more than one of these on the same set of axes, so as long as you get the rough shape of what tan looks like, you'll be fine. You don't really need to care about the differences between those dilation factors there. The one that kind of plays a role is going to be the n term. That's going to be whatever the multiplication is on the x variable. That is going to adjust the period of the tan graph, but if you do things the way I do it, you won't actually ever care about what the period of the tan graph actually is, unless the question asks you, which of course then you calculate. But again, if you follow the procedure that I'll outline, it won't actually end up mattering. So yeah, just a few key takeaways. That the a value, the coefficient at the front, isn't really going to matter too much when it comes to sketching it by hand. The n value is going to be used in calculating the period, and it does have an impact on the spacing of your graph, but we're not going to really need it unless you are specifically trying to calculate the period. So let's have a look at an example. These are the steps that you need to follow, so long as you just have the dilation factors. I'm proposing that you find the asymptotes by solving a circular function rather than by learning a full new set of equations to solve those. How does this work? Tan, by definition, is sine divided by cos. And at the beginning of when we were covering this, I mentioned that the asymptotes always occur when the denominator of a function goes to 0. So if tan is sine divided by cos, cos is now your denominator. So if you want to find the location of the asymptotes, you solve for where cos is equal to 0. This looks like a decent amount of work and lines are working out, but it is very, very repeatable because you're always solving where cos goes to 0, and cos always goes to 0 at the exact same spots every single time. It's always going to be plus minus pi on 2, and if you need to go further, plus minus 3 pi on 2. Right, you just continue to add 2 pi to your set of solutions over and over again from there, and you'll get all the possible solutions. You just keep going, adding or subtracting until you fill out your full domain. That's pretty much it. So what that actually looks like is, whatever the tan is, in this case it's tan 2x, you simply just replace the word tan with the word cos. Keep the brackets the same. This is a skill you guys should already have. You need to have it for your exam and definitely your SAC. And so rather than learn a new set of equations and apply those, you can use an old skill that you already have and should have as good. So that gets us our set of vertical asymptotes. From there, we find our x-intercepts. So for simple tan graphs, the x-intercepts will be the midpoints because there's no vertical translation. If you see where the inflection point is, it always occurs dead center, and because there's no vertical translation, it's not only dead center, but it's also resting on the x-axis itself. So you have a couple of different options as to how you find those. You can either solve f of x equals 0, which is what you do for literally every function ever. Doesn't matter if it's tan, sine, cos, logarithm, exponential, same thing. But because of the simplicity of this kind of question, you can also find the midpoints as well. So if we knew from earlier our asymptotes were plus minus pi on 4, the midpoint of that is 0. And so that's where the next intercept would be. The next set is pi on 4 and 3 pi over 4, the midpoint of which would be 2 pi on 4, which simplifies to pi on 2. So that's the easy way to do it. Alternatively, again, you can just solve another circular function. It's not too hard. You do need to have this skill anyway, so when you're doing a practice, it might actually just be worthwhile for you to practice solving tans, because this is one of the only places where you do get additional practice solving tan. Usually most of the solving circular function stuff uses sine or cos, so it's good to remember or get practice with solving your tan values specifically. For those of us who are new, by the way, I also do have created a tan unit circle. Like you guys will be familiar with the regular sine and cos unit circle, which is this one. It's got those set of coordinates. Just for your own reference, I also created a tan one as well that has the tan values on them. But okay. So up until this point, we've got our asymptote locations, we've got our x-intercepts. All we need to do now, well, I guess you also want to find your endpoints, which is just a matter of looking at your domain and then shoving in the values. Right? This had a domain of negative pi to pi, so if we didn't already know what was there, which we do, we know they're x-intercepts, if we didn't already know that, we would just shove that into the function and then evaluate that. And then finally you just plot. So depending on the reflection terms in here, it might start from bottom left to top right, or it might go from top left down to bottom right. Works exactly the same way as a cubic, by the way. So if you're already good with your cubic graph shapes, then apply the exact same principle to the tan graph. Tan being positive is like a positive cubic. Tan being negative is like a negative cubic. Any questions with that one so far? Cool. Kind of already touched on the reflections just briefly at the end there. One thing I should follow up on further is because of the nature of tan being well, mostly the basic tan is an odd function by definition. What that means is whether you reflect it in the x-axis or in the y-axis, see that the negatives are in two different spots, you actually get the same overall shape. The cubic also does this. And so that therefore follows if both are negative, then you actually just get right back to where you started. So when it comes to identifying whether you're starting bottom left or starting top left, it's just going to be a matter of where the reflection term is and how many of them there are. So if you have no reflection terms, it'll be basic. If you have one reflection term, it'll go from top left down to bottom right. If you have both, that's the same as having none. Cool. Next up are the translation factors. These work the exact same way as all your other kinds of functions. This is where you have an x minus h for your horizontal translation, and you have a plus c at the very end for a vertical translation. Again, just like your other functions, if you have minus a value, you are shifting right by that value. So if you have x minus pi on 2, you're now shifting right by pi over 2. Effectively, what this will mean is all your key features are going to be shifted right by pi on 2, where they otherwise would be. That's there just to show you or tell you what's actually happening. In reality, if we look at our procedure, we're not going to give a shit. It's just going to be solving where cos goes to 0. Yeah? Question?
Sorry, could you quickly scroll up a tiny bit so I can copy down just this? Yeah, give me like 2 minutes.
Yeah, sure. Let me know when you got it. But yeah, so this is the, basically you can think of this as the fully generic form of the tan graph. You now have both dilation factors and you have both translation factors. Now, yes, that is shifting it horizontally. If you have minus, it shifts right. If you have plus, it shifts left. If we look at the procedure, when it comes to solving our asymptotes, we're just solving cos equals 0, which will already have this term in there. Right, you'd be essentially solving cos x minus pi over 2 equals 0. And when it comes to solving your x-intercepts, well, unless you have a vertical translation, you're still just doing midpoints. So this is more so just for your own conceptual understanding of how that works. You got that copy down yet?
Yes, thank you.
Yeah, no worries. Here's what I was talking about with the plus shifting left. You'll see all those key features are now left by pi on 3. Actually, to make life easier, what I'll do is I'll just drop this whole document in the chat, so if I go too fast on the things, be able to copy it from there. Here's the vertical translation related stuff. So this one does end up mattering a little bit, actually. More so, it does end up mattering, in the sense that whatever your vertical translation is, you can think of as the y value of where your inflection point is going to be. So normally it inflects in the dead center and on the x-axis. Because we're shifting up by 1 in this circumstance, now you can see the y-coordinate of all of those inflection points is now 1. It's still dead center of the asymptote pairs, but now it's shifted up. The reason that matters extra is because if you now look at where your x-intercepts are, those are no longer in the dead center anymore. They're all now offset by a certain amount, which means we can no longer just do the midpoint of our asymptotes, because if we do that, we're going to be off by a little bit. We're going to miss them. Which is why when you now have vertical translations, you'll see that in that procedure, there is no longer a section in there that says you can do midpoints anymore. So in that way, when you have a vertical translation on tan, it's kind of like your worst case scenario, because you have to actually do some more math rather than just very simple midpoint related stuff. So this is the updated and heavyweight way to do any tan graph that you come across. More steps because there are more complexities to it, but each individual step is quite simple. I've given you a nasty one as an example, not necessarily because that's what you'll get, but because if you can handle this kind of question, then you can definitely handle any of the other ones. For reference, at least Unit 1 and 2, this is what they're giving you in the textbook. You're getting dilation factors and literally 0 translations in there actually. They got, they got vertical translations, just no horizontal translations. So Unit 1 and 2, they're not asking much. Unit 3, 4, they might do both a horizontal and a vertical. And your SAC might go above and beyond to try and make things more complicated if you guys are still doing your circular function SACs. But okay, here's how you handle the nightmare question. For those of you who aren't already familiar, pretty much every guide that I have on sketching starts with this, which is get your graph into the general form. And what I mean by that is get it into a state where you can clearly see what all the key features of that graph are, the key transformation factors of the graph. For instance, the key offender here is going to be the 3x plus pi. I see this all the time when it comes to mistakes. People will look at this and think, oh, that's a shift left by pi, because it's plus pi. That is not quite true. Whenever you have a coefficient on the x, what that's doing is effectively hiding what your true horizontal translation term is. What you need to have happen is factorizing out any coefficients on the x, which will thus reveal what your true horizontal translation is. That's more or less the way I'll think about it. The math underlying what's actually going on is a little bit different, because fundamentally all you're doing is offsetting where the brackets go to 0. And because there's dilation factors happening, it's just changing where your brackets go to 0, and so on and so forth. But that's a bit more complicated to think about. So the reality is, as long as you just take the bracket, the coefficient off of the x and fully factorize what you have, you'll be in a good spot. So now we can see where all these are. We know we have a shift left by pi on 3, we know we have a shift up by 2, we know we have a couple of dilation factors, and we know we have a reflection in there. So if you're doing like an investigation SAC and it's like, what are the transformation terms in this, or how would they change the graph, you can now more clearly state what's going to happen if you modify any one of these things. Not going to matter so much for the sketching, because if we look at the procedure, we'll see that next step, at least when it comes to finding asymptotes, is going to be to effectively replace the tan with cos, and then just solve where cos goes to 0. Again, this is because you're essentially finding where the denominator goes to 0, which gives you asymptotes. So you strip off anything outside of the tan itself, replace the word tan with cos, keep the brackets the same. Set that equal to 0, and solve as you would for the other circular functions. This is a kind of complicated one, so what I'll typically do is do a substitution approach to make life look a lot simpler. It does take more work to bring it into this simpler form so you can understand it a bit better, but I think it's worth it because I'd much rather be solving this than that. It looks like a lot more complexity. So what's actually happening here is I basically just take whatever's on the inside of my cosine and replace it with a single letter. We saw an idea of that at the very beginning, actually, when I was replacing the inside of our logarithm. Now, what that does is, that means you now have cos of u equals 0. You have this, which looks nice and neat. What hasn't happened yet is fixing up the domain. One of the issues with these kinds of questions is no one really knows when do I stop finding solutions, right? How many solutions does actually fit between negative pi over 2 and pi over 2? Especially when there's all this sort of stuff going on, it's hard to tell. So my run around that is to, rather than have an x domain, put it in terms of this u domain. What that means is, you have this equation, which relates x to u. You have some x values. If you want to convert those x values to u values, you shove in the x values into the x spot, and whatever that simplifies down to is now a u value. So you go from having complicated x equation to simpler u equation. That's the idea. So you shove in negative pi on 2, and funny enough, negative pi on 2 does actually come back out in this case, but if you shove in positive pi on 2, you're going to get 5 pi on 2, both of which are going to appear as our new upper and lower of the domain. From here, because it's again just solving where does cos goes to 0, it's going to be plus minus pi on 2 and plus minus 3 pi on 2, so on and so forth. So you're just going to keep adding or subtracting your 2 pi n off of both of those terms until you fit everything within the domain that you have. That gives you a bunch of solutions, which would be the location of the asymptotes. Only challenge is, because we replaced our variables, we need to put them back now. So we know that u is equal to 3 bracket x plus pi on 3, so we're going to do exactly that. Chuck it back in. Now, this is more than anyone's going to ask you to do. What it would essentially be doing is getting the x back on its own. Usually you'll have either a multiplication or a plus or minus, not both. Again, this is just giving you the worst case scenario. Ultimately, all we're doing is getting the x back on its own, which in this case would be a matter of dividing everything by 3 and then subtracting pi on 3 from all those things. Again, you're not going to have to do this, very unlikely unless your teacher really hates you, but that is the overall procedure. And we get our asymptotes. Any questions there? Okay, next up, getting our inflection point. So the x-coordinate of it is always going to be dead center of our asymptotes, so that's fine. All we really need to care about is where the y value is going to be, and that's going to come from the vertical translation. We're shifting up 2, so the y value is now going to be 2. Nice and easy. From here, looking at reflection terms, there's only one of them, so rather than being a positive cubic, it's going to be a negative cubic shape. Going to go from top left down to bottom right. Finally, axes intercepts. So just like any other function, x equals 0 and y equals 0 is going to be your friend here for solving those. Y-intercept is the easiest, simply because everything simplifies quite quickly. So as long as you know what tan of pi is, which if we just have a quick look, that's pi on the tan circle. Tan of pi is going to be 0. So that all simplifies down to 0, cancelling that out, leaving you with just y equals 2. X-intercepts, a decent amount harder. We're again going to use that substitution approach to make this not look like hell. Y equals 0, get the tan on its own, and then yeah, simplify things from there. This is the substitution approach. The math is going to look awful for it, but as long as you understand like from here down, that's basically enough, because this level of complexity, it's more than you'll need. And then yeah, let's just say we simplify it all the way down. We get down to those as our x-intercepts. So what we're going to do is put all that information that we just found on our axes. We'll set up our asymptotes first, usually, and this dotted blue line here is more so just for your own visual aid. You don't actually necessarily need to include that in when you're doing it yourself to submit. It's just there more or less to show you, hey, all these inflection points are occurring at y equals 2. So yeah, we got our asymptotes. From there, I would then draw the shapes of the graphs themselves, and only then will I write in what the x-intercepts are. Because if you do the x-intercepts first, and then try to draw your graph, you might miss it. And then you're like, well shit, now I've got to rub it out and hit it again. So draw your grid lines first, then the curve in the middle, and then label what the intercept is. That'll be the easiest order to do this in. That's tan graphs. So you've seen the most complicated one just there. That's pretty much it for this bit. We'll get into some practice questions together, which will look a lot easier. But before I do, were there any questions about how this works? Cool. Okay, so I've given a screenshot of the summary, the steps that we follow when it comes to sketching tan. We're going to have a go. So let's see, sketching the graph. Let's try Now, I know some of these are actually kind of busted. Like for instance, this one here, you can't really do because there's no spot on the unit circle for where that has a solution. So let's go ahead and sketch, well, these are solvable, so maybe we'll do something like this. Okay. Actually, let me change up the brightness. Make it much easier to see that. Cool. Okay, we'll do y equals 3 tan 3x plus root 3. That's what we're going to be sketching, and we're doing it from negative pi to pi. X is an element, negative pi, pi. Cool. That's all written down for now. On the screen share, I will hold up the procedure that we follow for them, or you have a copy in the chat as well, should you wish. Let's have a go at solving it. Or sketching it, rather. What are we going to do? Step 1 says rearrange into the general form. Is there anything that has to be done here? General form just means making sure we can clearly see all of the transformation factors that are involved. So as long as we can see all the transformation factors that are involved, we don't really need to do anything here. We can see there's a couple of dilation factors, and we got our vertical translation. So we're going to go ahead and just skip that step 1 there. Next up, finding the asymptotes by solving cos equals 0 over the domain. What's that going to look like? Okay, so if we have a look back at the steps, we're up to step 2 right now. Find the asymptotes by solving cos equals 0. Now I've kept the terms inside the cos the exact same as the terms inside the tan. If you have a look back at the screen share, you'll see it's tan nx take b, and it's cos nx take b. So what that ends up meaning is whatever your tan says, which in this case our tan says tan 3x, we're now going to solve cos 3x equals 0. So what it looks like in practice is, if we go back to the handwritten bit, whatever the tan is, you rip that out on its own and replace the word tan with the word cos. All you do from there is make that equal to 0. And we're solving over this domain, negative pi to pi. Who remembers how to solve circular functions? I'll pull up the unit circle if we need that, because that'll matter a lot. Okay, when it comes to solving circular functions, what we're essentially doing is comparing the function or the equation that we have to the relevant spot on the unit circle. So fundamentally this is just cos equals 0. So what that means is I want to figure out on my unit circle where are all the spots where cos is equal to 0. Now as a refresher, cos is always the x coordinate on a unit circle, sine is always the y coordinate on a unit circle. So if I go back to like the beginning of this chapter in the screen share, you'll notice that the unit circle, radius 1, centered on the origin, any coordinate on the circumference of that circle is going to have you can essentially create some sort of triangle out of it. You have a hypotenuse, which is always equal to 1 because it's a unit circle. You have an adjacent side and you have an opposite side. The reason why those are sine and cos respectively is because of the trig ratios and the fact that the hypotenuse is 1. Right? So if you think about sine being opposite over hypotenuse, if hypotenuse is just 1, then that means the opposite side, this side, is just the length of that is just sine, because the hypotenuse is now 1. So if we look at what that means as far as coordinates go, that's a vertical height. And vertical on an x-axis, on an axis just means it's the y value. Hence the y value is sine. Exact same logic follows for cos. So again, as a refresher, cos is always the x coordinates, sine is always the y coordinates. So when it comes to finding where does cos go to 0, we want to know where the x coordinates on our unit circle are 0. I said this earlier, they're always in the exact same spot, plus minus pi on 2, plus minus 3 pi on 2. And you can keep going until you fill out your full domain. So what I was looking at there were these, right, the actual coordinates themselves. This is x equals 0, this is x equals 0, and these are the angles where they exist. That's what we write down as our answers. So what that looks like, if we go back to the handwritten bit, you take whatever's on the inside of the cos, which in this case is 3x, and you make it equal to those solutions. Plus minus pi on 2, plus minus 3 pi on 2. You don't really have to have the plus minuses just now. I'm kind of just saving time there because that gives you more solutions ahead of time. You can start with just pi on 2 and 3 pi on 2 and then continue from there. At this stage, I would start rearranging to get the x back on its own. So that will be a matter of dividing all these solutions by 3, giving you plus minus pi on 6, plus minus pi on 2. Because the 3's will cancel out from there. Do a quick check back with our domain. We'll realize, okay, we still got some room. Or at least it looks like we still have some room. Because we're currently capping out at plus minus pi on 2. We need to be capping out at negative pi, or plus minus pi. So we'll just keep adding on, which is a matter of adding 2 pi, or plus minusing 2 pi from both of these solutions. So if the sequence is pi, 3 pi, the next one would therefore be 5 pi. So if we then have a look at, again, dividing that 3 by 3, we now have plus minus 5 pi on 6, which I am reasonably confident is going to be the cap. Anything further than this will go over, but just to show what that looks like. 7 pi on 2, and then again dividing by 3, we now have 7 pi on 6, which of course is too big and too small. So we kill those. This is now our set of asymptotes. Right, we solved where our denominator was 0, where cos was 0. So because you get a lot of x equals stuff, it kind of pays off to just label what you actually did there. Label them as asymptotes. Because if you don't, you might get a bit confused with what's an asymptote versus what is a x-intercept. Because they both just say x equals something. So we just did our asymptotes. Next up, step 3, identify the vertical translation. This will find us the location of our inflection point. Hopefully someone's brave enough to say this one. There's a vertical translation here. What is it?
Is it root 3?
It sure is. Yeah, root 3. That's it. So it's going to be a shift up by root 3, which means all of our inflection points are going to be at root 3, or at least the y-coordinates of those are. Nice. So you can just like say y equals root 3 and remind yourself that way, or you can just have it in the back of your mind when you go to sketch it. You can be like, yep, cool, I know where those are going to be now. Step 4, identify the shape of the graph from the reflection terms. Well, first question we've got to ask is, are there reflection terms? And if so, what's the shape of the graph going to be? Can anyone help me there? Do we have any reflection terms? So yeah, think about graphs you guys might be more familiar with. You know, your quadratics, your cubics. Polynomials is usually what everyone's finished up until now, or at least just getting through by the end soon. Reflection terms just mean you have a multiplication of a negative in there somewhere. There are no negatives to be seen in the entire function, so we're pretty happy to say there are no reflection terms there. So what that means for the graph is it behaves kind of like the general version of the cubic, in the sense that it's going to start from the bottom left and from the top right. So we're going to be drawing essentially a bunch of these shapes over and over again. Almost there. Next up, finding our axes intercepts. So we need both our x and our y intercepts here. The y-intercept one, just as a bit of a pro tip here, because there was no horizontal translation, we're basically guaranteed to know that our y-intercept is going to be at √3. Because if we, yeah, you'll see when I draw the graph. So we're just going to go ahead and skip actually doing the y-intercept, and we'll go straight to the x-intercepts. Who can tell me how we find the x-intercepts of not just tan, but any function? How do we find x-intercepts of any function?
Set them equal to 0.
Set them equal to 0, precisely. Same thing works for tan. So in this case we have 3 tan 3x plus √3. We're now going to have 0 equals 3 tan 3x plus √3. And we're just going to solve this. So, as a reminder, how do we solve circular functions? First thing we do is we get the circular function on its own. It's going to be a matter of subtracting the √3 and dividing the 3. We can see the circular function is now on its own, and one of the unit circle exact values is on the other side. I mean, kind of, if we have a look at the tan unit circle. Oh no, I do actually have this version of it. There's two ways that could have looked. It depends on whether the denominator was rationalized or not. Just to give you an idea what that means, negative √3 on 3 could be rewritten in a slightly different way by multiplying the top and bottom of that fraction by whatever the root is. What you'll see is that'll turn out to be the √3 and √3 will cancel down to just 3, and the 3 and √3 will just remain 3 √3. Negative will come through, and then because you have 3 on top and on bottom, you now have -1 on √3. So if you see this, just know it is also this. These are the exact same thing. I've only drawn one on there. Maybe I should go ahead and update the pictures of these so they also include the rationalized version as well, because the sine and cos one also has similar issues. But yeah, as long as you recognize that it's unit circle related, you should be able to go one way or the other to make it more obvious which one's which. But okay, so we need to now know, where does tan equal negative √3 on 3? I have the tan unit circle up on the screen share. There's only one value for you to be looking for, negative √3 on 3. Where are the spots on the unit circle where we have negative √3 on 3? It's on the screen share. You're looking on the outer edge, so all of these. You're looking for when you hit negative √3 on 3, and all you're going to do is report what angle is there.
Is it 330 and 150?
330, 150. Yeah, 330 there, 150 there. Yes, those are exactly right. So those are the spots. What you would typically do, because our domain was in terms of radians, is you would typically give them in terms of the radians version, so 5 pi on 6 and 11 pi on 6, but you did find the right spots. That's the main thing for today. Just note that when you're doing this for yourself or during the SAC, you want to give the radians versions because your domain was in terms of radians. If, for instance, it said it was between, rather than negative pi and pi, it was between plus minus 180, then yeah, absolutely, you want to give those versions in degrees. But okay, so when it comes to finding our set of solutions there, let me just rub all this stuff out. Give us some space. Back to the handwritten bit. So again, taking whatever's on the inside of tan, and then those values. So we had 5 pi on 6 and we had 11 pi on 6. 5 pi on 6, 11 pi on 6. Again, getting the x back on its own is a matter of dividing everything by 3, which means we now have denominators of 18. That's pleasant. Again, we're still trying to fit this between, what was it, plus minus pi? Yeah, we're still trying to fit it between plus minus pi. So we need to continue finding more solutions beyond that first revolution. There might be another one in the forward direction, in the positive direction. There's definitely going to be some in the negative direction. Can anyone remind me how we find the other solutions that would fit within the domain? All good. Okay. So basically, once you have your first two solutions, it's effectively just a matter of adding or subtracting 2 pi. And the reason why is because 2 pi is a full revolution around the unit circle. And so when you start at a solution and add 2 pi to it, you basically just say, hey, I want to get right back to where I was, but the next revolution forward, or maybe the previous revolution if you're subtracting 2 pi. So we're just going to go ahead and do exactly that. Tan specifically is kind of cool because all solutions are separated by pi. So you could also, for tan specifically, keep adding or subtracting pi over and over again, and that'll also work. Where you do it's going to matter though. Don't do it here, you've already done the rearranging. Do it here and then rearrange what you get. So for instance, to keep going forward, it'd be a matter of adding pi a bunch of times. So getting into the same denominator, that would be 6 pi on 6. So you're basically just adding 6's here. That will get us 17 pi on 6, which would finally divide down to 17 pi on 18, which, hey, look at that. We did actually fit one more in there. Nice. From here, we're just going to find all the negative solutions. So it's going to be a matter of subtracting a bunch of pi's from this bit here. So 5 minus 6 gets us to minus 1. And we'll keep going. So that's going to be minus 7 pi on 6. We'll probably keep going as well. So 13 pi on 6. 14, 15, 16, 17, 18. Yeah, too many. And then finally, yeah, bringing those all over, 18. Those are all of your x-intercepts. So, when it comes to sketching this graph, it's going to be kind of nasty. But what it would be was, you do your asymptotes first. So this is like your plus minus pi on 6, plus minus pi on 2, plus minus 5 pi on 6. So another set there, there, another set there, there. Dot, 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 dot. Keep going, keep going. I'll just fill out the first couple, just for the sake of brevity. Is that what they were? Yeah, pi on 6's. Pi on 6, minus pi on 6. X-intercepts, so the one that's going to matter for us would be this one here, the negative pi on 18, minus pi on 18. And again, you would just keep listing all these out during those sections there. I've actually broken my own rule, which was draw the graph first and then draw out the x-intercept. So do as I say, not as I do, I guess. You get your cubic-like shape, and the inflection point was that too. Remember that from earlier. All you're going to do is keep repeating that for the rest of these. Right, you just draw a bunch of those. Oh, yeah, sorry, I should be inflecting up higher. You just draw a bunch of these over and over again in between all those spacings, and then each of these is going to marry up with one of the x-intercepts. That's the idea there. We've hit time, so we'll take a pause here. If there's any questions about how any of that's worked, feel free to stick behind. Happy to explain things further. Even if you had questions about other things, we'll see if I can help. Otherwise, I appreciate you guys coming, and I'll see you guys either tomorrow or next time I see you in class.
Thank you.
Thank you.
Thanks. Have a good day.
No worries. You too.
Have a good day.
You too. Thanks. Alrighty, and then there was one. Still with us, Diane? Got a question, or...? If you do, you're muted. Oh, there we go.